Hi y'all, this is a video getting back to graphs of functions. We want to go into a little more detail, look at similar things to when we did our intro to function notation, but slightly messier graphs and slightly more complicated questions, I think, crop up along the way here. So, very first thing we need to tackle is f a function? Remember that the rule is for a relation to be a function, every input has to get paired with exactly one output. So this is definitely a relation. This graph is relating x values and y values using ordered pairs points on the graph. So the point 6, 3 is relating an input to an output. And we're using function notation. We're calling it f of x, y equals f of x. But the question is, when we're looking at a graph, how do we really decide that that graph represents a function? So I think the trick to this is recognizing that an input is an x value on a graph. So we want to be able to visually isolate any x value on the graph. So say I'm interested in isolating x equals 5. X equals 5 is this entire vertical line. So this vertical line isolates the single input x equals 5. And every time this vertical line hits the function, we're pairing an output with that input. So the test for whether or not a graph represents a function is called the vertical line test. And it basically says a vertical line should not cross through the graph of a function more than once. If it hits it more than once, then that's more than one input paired with more than one output paired with an input. So if we visualize a vertical line, we move it across this graph, we would never want to hit the graph more than once. I would say we have one questionable spot. X equals 7 is questionable, but it turns out this is okay. The bottom open circle means there is not actually a point at 7, -1. The graph starts infinitely close to that and heads out, but we do not actually hit the point 7, -1. We do hit the point 7,5, but that's the only point we hit on this vertical line. So this is, in fact, a function. We can tell because it passes a vertical line test. Okay, so that was part A. Part B, we are supposed to find f of 0, f of 7, f of 2. This hopefully is really familiar, but this is a little bit messier function, so I just want to make sure we don't get thrown off when we have a piecewise function made up of different pieces. Okay, so f of 0, we're saying 0 is our input. If we go to our graph and choose the input 0, we're looking for where our graph crosses the y-axis, and it's right here at the point 0, 2. So this says if your input is 0, what is your output? And the answer is 2. Outputs are y values. F of 7, we actually just talked about this one. So just to make sure everyone's really clear on this, there's kind of a questionable thing happening when the input is 7. It appears that we're hitting the graph at 2 different locations, but the open circle actually indicates that we are not. There is no point here, so we don't actually hit anything down below the x-axis. The only point we hit on the graph is this one, 7, 5. So that says input of 7 will give output of 5 from function f. So the output is 5. F of 2, okay, so we go over to input 2. The only place we hit the function is at an open circle, which means we don't actually hit it at all. So f of 2 is undefined. Again, it would be okay to say does not exist or 2 is not in the domain of the function. Those are fine with me. We wouldn't want to say no solution here because there's no equation to solve. This is just asking what is your output when your input is 2, and the answer is I don't have an output for 2. Okay, last one, f of 7 minus f of 5 over 2. So this, I hope we're spotting, is a slope question or average rate of change, but I would say slope is fair here because between 5 and 7, the graph is actually linear. So it's not an average, it's the exact rate of change, which is called slope. Okay, so f of 7. F of 7 is 5. F of 5 is 1. And we're supposed to subtract and then divide by 2. So we're getting 4 over 2, which is 2. This is correct. This is great. I should point out that we don't actually have to do the plugging into the function and the arithmetic here, because if we've recognized already that it's slope, we could just say, oh, if I go over 1, up 2, over 1, up 2, that means I have a slope of 2. Same answer we got. Okay, next, I'm going to give you some outputs and ask you for inputs. So first, I'm giving the output 0. F of x equals 0 means your output or your y value is 0. And you are trying to solve for an input that would make that true. So even without me using the word solve, I hope you recognize this is a solve problem. Solve for x if the output is 0. Okay, so outputs are y values. We're going to look at y equals 0, which is the x-axis, and we're going to see where we hit the function. You can see I hit the function right here. So it looks like if x is roughly negative 0.7, then our output will be 0. It's fine to estimate. You'll have to estimate sometimes with the graphs. Just be careful. Next question is, what x values will give you an output of 2.5? So again, even if I don't use the word solve there, this is a solve. I'm solving for x. So what x values will make my output 2.5? So 2.5, all right, so we're looking right around here. And I see 3 different places where I cross the graph. So again, I'm fine with a little bit of estimating here. It doesn't look quite like we're over to 0.5, so I'm going to say 0.4. And then same thing here, it looks sort of symmetric, so I'll say it's a little over and it's 0.6. And then this one, if this has a slope of 2, that's 5.5, and that should be 5 3/4. Okay, so always look for all possible inputs. The function rule says one input should only get one output, but it does not say a single output will only pair back to one input. A single output compared to multiple inputs, and that's fine, and you want to make sure you found all of them if you're answering a question like this. Last one, f of x equals 6. So I'm looking at the y value of 6. I'm not seeing that I run into the graph at all. So this one, I would say no solution. Again, the distinction is just, was the initial problem asking you to solve or evaluate? Here I'm actually being asked to solve for x. So the appropriate way to say that that doesn't work is no solution. Just to point it out, look at this graph for a second, maybe pause and think about what you would say if I asked you to solve f of x equals -3. So again, pause if you want to think about it for a second. I would say -3 is my output. If I'm looking at what's going on here, I don't see that I hit the function at all, but we need to pay attention. There's an arrow on the end of this function, and it is a straight line. So I expect it to continue this exact same linear pattern forever, which means I do expect to hit y equals -3 if x equals 9. This is very different from up here at the top where I have a closed circle. That means the graph actually dead ends there. So putting arrows on the end of your graphs is important if you want to show that they continue. Same thing here. This is a closed circle, so I'm not assuming that the graph continues. Okay, for what values of x is f of x greater than 2? Let me grab another color here. So this again is a little bit more complicated question, but if you're reading it off correctly, I hope it doesn't give you too much trouble. Remember, f of x's are y's. So when I look at this, I say, okay, what x values make my y value bigger than 2? So here is a y value of 2. And I'm looking for all y values on the function that are bigger than this. So this little strip right here has y values bigger than 2. And this strip right here has y values bigger than 2. So if I want to describe this, I'm either going to use interval or inequality notation. I don't care which you use, just use one correctly, and you should understand both. So if I give you either of those notations, you should know what I'm saying. So let's see, maybe we'll do one of each. So for this one, let's do interval notation. So I would say my y is bigger than 2 if my x's are between 0 and 2, or if my x's are between 5.5 and 7. So interval notation, you always want to go smallest to largest. So my first interval is 0 to 2. I do not want to include x equals 0 because when x equals 0, y is exactly equal to 2, and I specifically asked for y is bigger than 2. So round bracket's going to leave out x equals 0. X equals 2, I'm going to use a round bracket. Again, I could say for the same reason, and also because the function does not actually have a point at 2, 2, so I definitely need to leave that one out. To say the or part of this thing, I said between 0 and 2 or between 5.5 and 7, you would use a union symbol. The union symbol, excuse me, joins two intervals together, and basically you get the combination of all points in either one of the intervals. Not to be confused with an intersection, which would be the upside down of this. Intersection is only the overlap between the two sets. So if you just want to combine a couple of different sets, use a union. Okay, so we want to start at 5.5. And we want to stop at 7, and we want to think about that round bracket, square bracket thing again. I don't want to include 5.5 because that makes my y value exactly equal to 2, and I want it bigger. I do want to include 7. I'm not stopping at 7 because my y value has gotten smaller than 2. I'm stopping at 7 because the graph actually stops there. And if I plug in 7, f of 7 is 5, which is definitely bigger than 2, so 7 is a solution. We should include it. So those open circles generally are going to give you round brackets, closed will give you square brackets, but again, you have to think about what the inequality says. So even if I had a closed circle here, I would still not include that point because it's not a solution to the inequality. Okay, so hopefully, so this is visible. I'm going to switch colors again. I also asked, when is f of x less than or equal to 0? So, whoa. Here is y equals 0. And again, when you look at this, f of x less than or equal to 0, that's what you should see. When is your y value less than or equal to 0? So we go along, here's y values equal to 0. We want anywhere we hit the graph with this line and anywhere that the graph is below this line. So we're going to get this section right up to here. And we're also going to get this section. We don't want to miss this. This is absolutely included. So this time I'm going to use inequality notation. In words, I would say that my y will be less than or equal to 0 if my x is between -1 and maybe -0.6, -0.7. And I would actually say or if I'm being careful with my math words here, or if x is bigger than 7. For any x value bigger than 7, we're going to be down here on this line segment, and our y's will be less than or equal to 0. So for inequality notation for this one, I would just write inequalities that represent that. I would say, okay, so any x between -1, I want to include -1, so I'm going to put an equal to. And I'm estimating here -0.7. And again, I want to include that point because now I want to know if my y is less than or equal to 0. So right at that point that I'm approximating, I hit the axis at, I want that part to be in my solution set. And then the union, if you're using this notation, would generally just be the word or. X is greater than 7. And I do not want to put an equal to because there's no point on the graph at 7, so that doesn't make sense. So I don't care if you're using inequality or interval notation. You should recognize and understand what both are saying, including the equal to, not equal to, and the round bracket, square bracket stuff, the ors, the unions. And you should be able to write one of those correctly to describe a set. Okay. Domain of f, let's continue to switch back and forth. Let's do domain with interval notation. And then we'll do range with inequality notation. But again, it's entirely up to you. You don't have to do it that way. It's just so that you can see some of both. So the domain of my function is about the set of all possible inputs. So if I'm looking at this, I want to think about, as I work my way across the x-axis, for what x values does this function actually pair a y value? So if you don't get a y value, you're not in the domain of the function. So I just like to work left to right here and say, okay, over here, if I look up and down, I'm not going to see the function, so I don't have a y value. In fact, I don't have a y value until I get to -1. So starting at x equals -1, I am in the domain of the function, and I continue to be in the domain of the function until I hit x equals 2. So there's something important happening here. When I look up, this is an open circle, so I don't see anything, which means I am not in the domain of the function. Okay, so the first part of the domain is all x's from -1 to 2, and we don't want to include 2. So if we're doing interval notation, I would say starting at -1, stopping at 2. -1 is included, so it gets a square bracket. 2 is not included, so it gets a round bracket. Okay, and then everything from 4 to 7 looks good. So notice I don't have any y values between 2 and 4. Instead of saying that violates our exactly one function rule, we just say let's leave that out of the domain. If you don't get an output, it's not in the domain. So starting up again at 4, I'm in the domain of the function, and then I hit a dead end at 7, but the function doesn't actually dead end there. So at 7, I look up, I see the graph, I'm still in the domain. If I step over even a tiny bit from 7, I stay in the domain of the function because now when I look down, I can see the function. So the function doesn't actually skip any x values from 4 all the way to infinity. This goes forever, so we're not going to stop. So there's no reason to write this segment with its own chunk of the domain and this segment with a separate chunk. The only reason you need to split your domain up into separate intervals is because you actually skip some x values. So here I'm going to say I want to combine that with all the x values starting at 4 and going forever, so going to positive infinity. 4 is a closed circle, so it gets a square bracket. There is actually a point at 4. The idea with infinity is that you can never actually get there, so we always give infinities a round bracket every single time. Okay, and then last one here is range. This is a question about set of all possible outputs. So we're thinking y values, and I approach it in sort of a similar way. I imagine just working my way bottom to top up the y-axis, and anytime I look left and right and see the graph, that means that I am actually getting a y value at that point. So starting from negative infinity, I'm going to see this piece of the graph when I look. It's really far to the right, but if I look far enough to the right, I will run into this segment of the graph. So this actually goes forever in the negative direction. So I'm going to start from negative infinity, and then I want to see when I actually start to miss some y values. So as I get up to right here, I should question, because I've been looking over at this part of the graph and all of a sudden it dead ends. But if I look the other direction, there is actually a point. So y equals -1 is in the range. And things just above that continue to be in the range because now I can see this little parabolic piece of the graph. So as I work my way up, I can see over here, over here, over here. I'm standing right on top of the graph. I can see over here. And then when I get to the top of this parabola, I should stop and ask myself again, I'm appearing to get a biggest y value at y equals 3. So if there is not something that takes over from there, I would want to stop that interval of my range. But I actually do, once again, if I step up from this just a little, still see the function, because now I'll be able to see over and realize there's a piece of the graph over here. So really, my range goes all the way up to y equals 5 with no interruptions. So I want all y less than or equal to 5. That's how that would look in inequality notation. So the inequality notation is kind of nice for things that go on to infinity because you don't have to write that. That's assumed in a statement like this. If you want to be a little more formal, you could make this set notation. So you could tack on just a little bit. The squiggly brackets mean the set of. So I would look at this and say, okay, this is the set of all real numbers y such that is the vertical bar. Y is less than or equal to 5. So it's just a little more complete and formal statement. I am fine with just the inequality, but I do want you to be aware of set notation in case you get in a class where someone really values using the formal notation. All right, that's it for this one. Thanks for watching.